3.2 Properties of the rock for the Z-transform. The examples of the previous section suggest that the properties of the rock depend on the nature of the signal. These properties are summarized in this section with some discussion and intuitive justification. We assume specifically that the algebraic expression for the Z-transform is a rational function and that xn has finite amplitude, except possibly at n equals 0, 0 or n equals -0, 0. Section 3.2 Properties of the rock for the Z-transform. Property I. The rock will either be of the form 0, RRLT ISL, or ISL LTRL 0, 0, or, in general, the annulus, i.e., 0, RRLT ISL LTRL 0, 0. Property 2. The Fourier transform of xn converges absolutely if and only if the rock of the Z-transform of xn includes the unit circle. Property 3. The rock cannot contain any poles. Property 4. If xn is a finite duration sequence, i.e., a sequence that is 0 except in a finite interval OOLT NL n and 2LT 0, 0, then the rock is the entire Z-plane, except possibly Z0 or Z equals 0, 0. Property 5. If xn is a right-sided sequence, i.e., a sequence that is 0 for NLT 0, 0, the rock extends outward from the outermost, i.e., largest magnitude, finite pole in x, z, 2, and possibly including, z equals 0, 0. Property 6. If xn is a left-sided sequence, i.e., a sequence that is 0 for NGT and 2GT-0, 0, the rock extends inward from the innermost, smallest magnitude, non-zero pole in x, z, 2, and possibly including, z0. Property T. A two-sided sequence is an infinite duration sequence that is neither right-sided nor left-sided. If n is a two-sided sequence, the rock will consist of a ring in the Z-plane, bounded on the interior and exterior by a pole and, consistent with Property 3, not containing any poles. Property 8, the rock must be a connected region. Property 1 summarizes the general shape of the rock. As discussed in section 3.1, it results from the fact that the condition for convergence of EQ 3.2 is given by EQ 3.7, repeated here as L009NLLRNLT00, 3.30, n equals 00 where R equals ISL. Equation 3.30 shows that for a given xn, convergence is dependent only on R equals ISL, LE, not on the angle of Z. Note that if the Z-transform converges for ISL RO, then we may decrease R until the Z-transform does not converge. This is the value IZ equals RR such that 9NLRN grows too fast, or decays too slowly, as n to 0, 0, so that the series is not absolutely summable. This defines RR. The Z-transform cannot converge for R RR since Rn will grow even faster. Similarly, the outer boundary RL can be found by increasing R from RO and considering what happens when n to -0, 0. Property 2 is a consequence of the fact that EQ 3.2 reduces to the Fourier transform when ISL equals 1. Property 3 follows from the recognition that x, z, is infinite at a pole and therefore, by definition, does not converge. Property 4 follows from the fact that the Z-transform of a finite length sequence is a finite sum of finite powers of z, i.e., nzx, z, equals lx and zn. N equals nl therefore, 9, z, 1 lt 0, 0 for all z except z equals 0 when n2 gt 0 and / or z equals 0, 0 when nl lt. 112 Chapter 3 The Z-transform properties 5 and 6 are special cases of property 1. To interpret property 5 for rational Z-transforms, note that a sequence of the form nxnlak, dk, nu n, 3.31, k equals L is an example of a right-sided sequence composed of exponential sequences with amplitudes ak and exponential factors dk. While this is not the most general right-sided sequence, it will suffice to illustrate property 5. More general right-sided sequences can be formed by adding finite length sequences or shifting the exponential sequences by finite amounts. However, such modifications to EQ 3.31 would not change our conclusions. Invoking the linearity property, the Z-transform of Xn in EQ 3.31 is NAKX, Z, equals L1, 3.32, K equals L isa GT. It'll note that for values of Z that lie in all of the individual rows, isa GT I don't know I, the terms can be combined into one rational function with common denominator NTI, 1 dkz1, K equals LIE, the poles of X, Z, are located at ZdB, dn. Assume for convenience that the poles are ordered so that dl has the smallest magnitude, corresponding to the innermost pole, and dn has the largest magnitude, corresponding to the outermost pole. The least rapidly increasing of these exponentials, as n increases, is the one corresponding to the innermost pole, i.e., dl, and the most slowly decaying, or most rapidly growing, is the one corresponding to the outermost pole, i.e., dn. Not surprisingly, dn determines the inner boundary of the rock, which is the intersection of the regions isa gt idcl. That is, the rock of the Z-transform of a right-sided sum of exponential sequences is isa gt I dn I max idcl equals rr. 3.33, k.i.e., the rock is outside the outermost pole, extending to infinity. If a right-sided sequence begins at 2 nt-lt0, then the rock will not include is equals 0, 0. Another way of arriving at property 5 is to apply EQ 3.30 to EQ 3.31, obtaining n at ak, dk, near dash colon colon, t iacl, ith/rl, lt00, 3.34, which shows that convergence is guaranteed if all the sequences id/rln are absolutely sum maybe. Again, since IDNI is the largest pole magnitude, we choose IDN/RLLT1, or RGT-IDNI. For property 6, which is concerned with left-sided sequences, an exactly parallel argument can be carried out for a sum of left-sided exponential sequences to show that the rock will be defined by the pole with the smallest magnitude. With the same assumption on the ordering of the poles, the rock will be isl lt idle equals min idl rl, 3.35, k. ORM section 3.2 for 31, 1 mded lees are 0.32, can the lost east the it is, 0.33, ise, ling.34, tli l, or alel how arn 1.35, properties of the rock for the two transform i.e., the rock is inside the innermost pole. If the left-sided sequence has non-zero values for positive values of n, then the rock will not include the origin, z0. Since xn now extends to -0, 0 along the negative n-axis, r must be restricted so that for each dk, the exponential sequence, dkr1, n decays to 0 as n decreases toward -0, 0. And for right-sided sequences, the rock is dictated by the exponential weighting r required to have all exponential terms decay to 0 for increasing n. For left-sided sequences, the exponential weighting must be such that all exponential terms decay to 0 for decreasing n. Property 7 follows from the fact that for two-sided sequences, the exponential weighting needs to be balanced, since if it decays too fast for increasing n, it may grow too quickly for decreasing n and vice versa. More specifically, for two-sided sequences, some of the poles contribute only for ngt0 and the rest only for nlt0. The rock is bounded on the inside by the pole with the largest magnitude that contributes for 11 gt0 and on the outside by the pole with the smallest magnitude that contributes for nlt0. Property 8 is intuitively suggested by our discussion of properties 4 through 7. Any infinite two-sided sequence can be represented as a sum of a right-sided part, say, for n::, 0, and a left-sided part that includes everything not included in the right-sided part. The right-sided part will have an rock given by 3.33, while the rock of the left-sided part will be given by EQ, 3.35. The rock of the entire two-sided sequence must be the intersection of these two regions. Thus, if such an intersection exists, it will always be a simply connected annular region of the form RRLT is LTRL. There is a possibility of no overlap between the rows of the right and left-sided parts, i.e., RLLTRR. In such cases, the Z-transform of the sequence simply does not exist. Example 3.7 Non-overlapping regions of convergence. An example is the sequence 1, 1. XNL2 earn 3 UN-1. Applying the corresponding entries from table 3.1 separately to each part leads to 1 1x, z, equals plus 1. 1 1 plus 3 z1 is LGT is LT. Since there is no overlap between ISA-GT and ISA-LT, we conclude that Xn has no Z-transform, nor Fourier transform, representation. As we indicated in comparing examples 3.1 and 3.2, the algebraic expression or pole zero pattern does not completely specify the Z-transform of a sequence, i.e., the rock must also be specified. The properties considered in this section limit the possible rows that can be associated with a given pole zero pattern. To illustrate, consider the pole zero pattern shown in figure 3.8, a. From properties 1, 3, and 8, there are only 4 possible choices for the rock. These are indicated in figures 3.8, B, C, D, and E, each being associated with a different sequence. Specifically, figure 3.8, B, corresponds unit circle TM Zeep Jane A B C Re, A, TM Zeep Jane C Re, B, C, TM Zp Anna, D, E. Figure 3.8 examples of 4 Z-transforms with the same pole zero locations, illustrating the different possibilities for the Raj, each of which corresponds to a different sequence, B, to a right-sided sequence, C, to a left-sided sequence, D, to a two-sided sequence, and E, to a two-sided sequence. 114. Section 3.3 The inverse L transform to a right-sided sequence, figure 3.8, C, to a left-sided sequence, and figures 3.8, D, and 3.8, E, to 2 different two-sided sequences. If we assume, as indicated in figure 3.8, A, that the unit circle falls between the pole at Z equals B and the pole at ZC, then the only one of the 4 cases for which the Fourier transform would converge is that in figure 3.8, E. In representing a sequence through its Z-transform, it is sometimes convenient to specify the rock implicitly through an appropriate time domain property of the sequence. This is illustrated in example 3.8. Example 3.8 Stability, causality, and the rock. Consider an LTI system with impulse response Hn. As we will discuss in more detail in section, the Z-transform of Hn is called the system function of the LTI system. Suppose that H, Z, has the pole zero plot shown in figure 3.9. There are 3 possible rocks consistent with properties 1 to 8 that can be associated with this pole zero plot, i.e., ISL LT, LT ISL LT2, and ISL GT2. However, if we state in addition that the system is stable, or equivalently, that Hn is absolutely summable and therefore has a Fourier transform, then the rock must include the unit circle. Thus, stability of the system and properties 1 to 8 imply that the rock is the region LT ISL LT2. Note that as a consequence, Hn is two-sided, therefore, the system is not causal. I'm Z-plane unit circle figure 3.9 pole zero plot for the system function in example 3.8. If we state instead that the system is causal, and therefore the Thn is right-sided, property 5 would require that the rock be the region ISA-GT2. Under this condition, the system would not be stable, i.e., for this specific pole zero plot, there is no rock that would imply that the system is both stable and causal.